Hi again. I hope you have so far enjoyed the review of Module 2 that we have provided for you. Here we want to actually look at the Module 2 in terms of the astrolabe for the 225 course that we have introduced before. If you remember, we have shown that different topics in this course are all outlined in this kind of circular geometry or astrolabe. What we have as the most outer layer is the very much most, I would say, underlying principles in math and physics that we touch on or we use. The second layer are the more relevant and related physical aspects that we are using directly in some of the concepts in this class. And the radial lines that connect it to the overall theme, which is the Cauchy equation of momentum, are basically the connecting lines that tell us with what approximation or with what which branches we are actually connecting these together. Module 1, which was the top part of this astrolabe, shown with the background color blue, was already covered. What we really covered in Module 2 is the red side, which is shown on the right-hand side. And to really look at it, we need to zoom more and see what really we had there. So let's zoom more and go through that step by step. If I look there, I can see that certainly there are some interesting concepts covered. First, we have second-order PDEs, and basically that's the place that we talked about exact solutions to Navier-Stokes equations and different boundary conditions that we have to deal with. We dealt with different types of problems, things like wall-driven flows or pressure-driven flows, so-called Couette and Poiseuille flows, and we had also combined flows. If you remember, as a drawing here, we can have a case where the lower wall has a certain velocity and is moving the liquids, for example, against a certain pressure gradient. The overall velocity distribution there is a combined velocity distribution that has a Couette-like nature, which is the linear part, plus a pressure-driven one, which is very much similar to the distribution you saw in the Poiseuille flow. Now, after covering that part in Module 2, we move to the idea that a lot of times in these cases, the final answers that we get mathematically can be reorganized in a way that we can get rid of units and make them dimensionless. We notice that this idea of dimensionless parameters, or in simple words, dimensional analysis, is not only limited to those type of problems. It can also be applied to many other types of problems, basically any problem in terms of physical aspects, and that's the part that really helped us to understand things, for example, in different limits of Navier-Stokes equation. When Reynolds number is much smaller than 1 or much larger than 1, we saw that different forces are important. For example, in the scaling of drag force that a sedimenting particle or a falling particle will feel in a fluid, we notice that at low Reynolds numbers, that drag force has a completely purely viscous nature, so it goes as mu times velocity of settling u multiplied to the diameter d. But at large Reynolds numbers, it goes as, or the scales with rho v squared multiplied to the area, cross-sectional area of the particle. So we clearly see that the dimensionless numbers and dimensional analysis can really help us to understand in what limits in terms of dominant forces we are really looking at the problem, and based on that, which other relevant parameters we should keep and which parameters are irrelevant and we can get rid of them. For example, at low Reynolds numbers, viscosity is important, but density or inertia of fluid elements is not important. So we can get rid of it and we get one dimensionless number remaining that will give us this type of a scaling. At large Reynolds numbers, viscosity is not anymore important, but inertia and density is the dominant case which we should keep, and based on that we get a different scaling which tells us that drag force goes as the dynamic pressure, that is a scaling with rho v squared multiplied to area. We also notice that dimensional analysis can help us think about different limits of Navier-Stokes equation. At the same time, there are certain simple cases of Navier-Stokes equation that can have basically no dominant scale in terms of geometrical scale given. And in fact, the problem of Rayleigh problem, we notice that in those problems, the dominant scale in the problem is actually evolving with time itself. So if you think about the similarity solutions and self-similar solutions, and what we basically did in Rayleigh problem, when you have the sudden impulsive motion of a wall, we have the diffusion of momentum inside our domain, and at different times this thickness of diffusion of momentum is evolving with time, and we actually need to scale the y-axis with a right combination of time with other parameters that are important, which here kinematic viscosity, y divided by square root of nu t, which is the right scale for delta of t, to find self-similarity solutions that will help us to solve these problems. Similarly, we notice that there are also cases where your domain is not anymore infinite, but actually is very, very much finite, and not only is extremely finite, it's extremely small. And those are the cases that we call the lubrication approximation. And we notice that the geometry is relatively complex there, so we cannot hope for exact solutions of Navier-Stokes equation. But this mismatch of the geometry and the fact that one gap, h for example, is much smaller than the other length scale L, helped us to find approximate expressions for our governing equations. And the governing equations, which are all branches of the overall Cauchy momentum equation, become simple enough that we can actually solve them in what we call lubrication approximation. And those solutions will give us accurate enough analytical answers. If you like to think about applied math language, really lubrication approximation is nothing other than the idea that in applied math people refer to as regular perturbation. Reynolds number is a perturbation parameter, so it's very small, and we only keep things that basically are proportional to the first order term. The second or higher order terms, we ignore them, and we solve the problem with this regular perturbation approach. These are all the concepts that we covered in Module 2, and I hope you have noticed that right now you have the tools to tackle a series of different problems based on the value of the dimensionless numbers, such as Reynolds number. You can see which tool or which approach or which approximate equation is the right way to tackle the problem that you have in mind. But still there is one part that is missing, and the question is what will happen when we are somewhere in the middle, when both inertia and viscous effects are important. And the other thing that can come in mind is what will happen to free surfaces. For example, so far we have really not talked about surface tension or capillary effects. These are all the things that we leave to cover in Module 3. So topics such as boundary layers, potential flows, when we have very high speeds flows in which vorticity and the dynamics of vorticity and the inviscid nature of the flow become really coupled together in an interesting manner, and also where this inviscid flow meets the solid boundary, which leads to the formation of a very thin viscous boundary layer. Those details are all the different aspects of Module 3 that we will cover very soon after Module 2. Plus, we will also have a small section that will talk about surface tension and capillary effects in fluid mechanics. I really encourage you to join us again in Module 3 and continue this journey with us in Module 3. I hope you have enjoyed Module 2 so far, and wish you all the best for the final exam.